And if you can, please turn on your cameras. All right, it looks like there's just a handful of us today. What's going on? People still popping in. I also know Scholar Showcase is starting, and at least I know Andrew's presenting this morning because we worked on that project together, but I wonder if others are doing the same. All right. Well, speaking of which, I know a lot of you, if not all of you, are doing some sort of presentation, especially for your, and correct me if I'm wrong, for your capstone projects you're presenting in the Scholar Showcase. So it would be great to support each other. So if you share like what sessions and stuff you guys are presenting in, so your classmates can go view the stuff. Because, I mean, it's kind of disheartening sometimes to present to like an empty crowd. I've done that before at a big conference, and then I was presenting in a small room with like 5 people. So, share each other's sessions so that hopefully you can attend each other's sessions. And of all the presentations being made, hopefully these are the ones that would make the most sense because you're all chemistry majors, right? So yeah. All right. So and I may have to leave just a couple of minutes early because I'm moderating a session at 11. So I'll probably have to leave a little bit early. All right, so let's do some recap. Last time we met, we finally started talking about spectroscopy. So let me make this. I have a million wires and they're all pulling. If I pull too hard, something will fall out. All right, so last time we met, we talked about spectroscopy. We introduced the idea of spectroscopy and how really spectroscopy is all about the interactions with light and matter. And so to understand this, we need to understand both light and matter. And we spend most of the semester talking about matter so far and how we can describe it using the Schrodinger equation and quantum mechanics. And then last time we met, we talked about some of those properties of light that are important for spectroscopy. And the first one is the energy of a photon is equal to h times the frequency, right? So this is the energy of the photon, and we need to take that into consideration. The second piece of property of light that we talked about that's going to be important was the fact that photons have a spin of 1, which means that they have an angular momentum. Let's use big S of square root of s into s plus 1 times h bar. And they have a z component of that angular momentum of either 0 or plus or minus 1 h bar. So photons of light have energies, photons of light have a spin and therefore an angular momentum. And then finally, we talked about how photons are oscillating electromagnetic waves, right? So when they interact with matter, that oscillation gets transferred into matter as well. And so we talked about how the intensity of any light interacting with matter will be proportional to something called the transition dipole moment m squared. And this transition dipole moment is equal to sort of the integral of some final state wave function with the dipole moment operator and then some initial state like that. So that's the transition dipole moment going from some initial state to some final state. There's the operator in the middle. That's just the shortened way of writing this, right? Final star mu initial d tau overall space. So those are 3 properties of light that we will, I guess I should move this over a little bit. The 3 properties of light that we will be interested in. When we talk about the energy, we want to talk about the conservation of energy. When we talk about spectroscopy, this light has an angular momentum, so we need to talk about the conservation of angular momentum. And it has this sort of frequency matching condition, which is not really a conservation rule, but probably should be one. Then we talked about all the various ways that molecules and electrons could move and how they're sort of energy scales, right? So energy scales for various motion, right? And so if we're going from low to high energy, right? We talked about how the lowest energy would be molecular translation, meaning just the molecule moving from one place to another, like zipping across a room. That's actually very low energy. Then there's molecular rotation. Above that is molecular vibration. And then above that is electronic transition, meaning the electron goes from one low energy state to a high energy state. For the molecular rotation, that happens in the microwave region of the IR spectrum. Vibration occurs in the IR region.
Hello there, Mr. King.
And I'm going to mute, there we go. And electronic transition happens in the UV visible region. And there are other kinds of things, other types of spectroscopy. We talked about NMR and that how that deals with changing of nuclear spin. We talked about EPR that deals with changing of electronic spins. And those are different transitions that interact with light. But for now, we're just going to focus on these four because we only have this lecture and one more. And I'll see how much of these four, or rather these three, because translation is boring, we can talk about. So let's talk about the second lowest on this list, because like I said, translation is boring. So we're going to talk about molecular rotation. So molecular rotation, or as we said, it's called microwave spectroscopy. I don't know if you actually did pure rotational spectrum before, but it would have been in the microwave region. I don't know if we have an instrument. Well, you have instruments actually that can do this. It's called a microwave. It's in your house or your dorm. All right, so for molecular rotation, the model that we're going to use is obviously going to be the three-dimensional rigid rotor, right? This is why we study it, because now we can apply it. So if you remember in the three-dimensional rigid rotor, the energy was L into L plus 1 times h bar squared over 2I, right? Where L was 0, 1, 2, 3, and so on. And I was the moment of inertia, right? Which was the reduced mass times this constant. So that was reduced mass. And that was the distance between the atoms. And this was, we call it the moment of inertia. But here's the thing. In quantum mechanics, we're already using L to talk about orbital angular momentum, right? L equals 0 is the s orbital, L equals 1 is the p orbital, and so on. But this has nothing to do with that. This is rotation. This is the whole molecule rotating. So we can't use L again, because then we're going to get confused. So what we're going to do, and you're going to have to erase these in your notes, I'm going to change L into J. Like that. Just to give it a different symbol. The problem is in science, we run out of symbols really quickly. We only have 26 letters in the alphabet and then 20 something in the Greek alphabet, and then we run out of symbols. We should use other language alphabets, actually. All right, so that's how we get the rotational energy of a molecule rotating in space. We use the model of a 3D rigid rotor. Pretty straightforward. All right, so now we need to use this model and the three different properties of light that we talk about and see how it all fits together. So the first one we're going to look at, actually, let me finish this up. So we know that the total angular momentum, right, for the 3D rigid rotor is J into J plus 1 times h bar squared. times the wave function. We've seen this before, so this is total angular momentum squared. So then the total angular momentum would be the square root of this part here, right? J into j plus 1 times h bar. And then there was a z component of the angular momentum, which would just be some, let's call it mj times h bar, where mj would be 0 plus or minus 1 plus or minus 2 all the way to plus or minus j. So I'm using j and mj instead of l and ml. Just because we're talking about rotation, we don't want to get confused with orbital angular momentum. So this is total angular momentum, and this is z component. All right, so these are all things we've done before. These are the properties of the 3D rigid rotor that we derived earlier in class. All right, so now let's make this all work with the 3 properties of light that we talked about. So the first one is going to be conservation of energy, right? So we know that any change in rotational energy should be equal to Planck's constant times the frequency of light. So when light comes in, this is the energy that it has. And so if that light gets absorbed by the molecule and it changes rotation, the rotational energy change should be equal to that, right? Any questions so far about that? So let's figure out what that change in rotational energy is. So we know, let's assume that the rotational change is, we go from some j initial state, ji, to some j final state, jf. Right? Those are the 2 numbers that we're going to change. So the change in rotational energy will be the energy for the final state, which would be jf into jf plus 1 times h bar squared over 2i minus ji into ji plus 1 over h times h bar squared over 2i. Right? Basically, I just took the energy here and just substitute final minus initial. I think we can simplify that just a little bit more. So the change in rotational energy would be jf into jf plus 1 minus ji into ji plus 1 all times h bar squared over 2i. Okay, here's my question for you. Calculate in terms of h bar squared and I, the energy differences between, let's do a few of them. Let's do ji equals 0 to jf equals 1. Let's do ji equals 1 to jf equals 2. And let's do ji equals 2 to jf equals 3. So spend some time trying to find those 3 different energy differences. when you have them, just type them in chat so that I know. So all we're doing is plugging in either 0, 1, 2, or 3 for JF and JI, right? In these three examples. And we're leaving our answers in terms of the constants H bar and I. So I would hope it's not too crazy. Do we have answers? I honestly thought this would take like 5 seconds each. All right, yep, we got some answers. Cool. So yeah, they come out to be these nice like integer multiples of h bar squared over I. So let's do the first one. So we're looking at the rotational energy change between 0 and 1. So JF is 1 into 1 plus 1 minus 0 into 0 plus 1 times h bar squared over 2I, right? 0 times anything is 0. 1 times 1 plus 1 is 2, so that's 2. So 2 minus 0 is 2. So this becomes 2 h bar squared over 2I, which is basically h bar squared over I, right? The second one, the rotational energy is it's going to be it's going from 1 to 2. So this is 2 into 2 plus 1 minus 1 into 1 plus 1 times h bar squared over 2I. So that becomes 2 times 3 is 6 minus 1 times 2 is 2 h bar squared over 2I. 6 minus 2 is 4. So this is 4 h bar squared over 2I, or basically 2 h bar squared over I. And then the third one becomes 3 h bar squared over I. So the energy difference here is 1 h bar squared over I. This one is 2 h bar squared over I. This one's 3 h bar squared over I. And you can imagine that pattern repeats. So if we're plotting this in a graph, let's say this is our energy, right? And here is our J equals 0 level. After h bar squared over I more energy, you get to the J equals 1 level. Then there's a double that distance for 2 h bar squared over I, and then we get to the J equals 2 level. And then for triple that distance, for 3 h bar squared over I, we get to the J equals 3 energy level. Now I wrote this like this, but here in the first level, there's only mj equals 0. But here there'll be 3 levels, right? With mj equals -1, 0, and +1, kind of like L and ML. Up here will be 5, 1, 2, 3, 4, 5 of those. Up here there'll be 7 of those, and so on. Right? But you know, they're degenerate. Okay, so we talked about the conservation of energy for rotation, and we see how that matches with the various energy levels for a rotational motion. What about conservation of angular momentum? That's the second requisite. Okay, so any change in the angular momentum. So let me just first write this again. Remember, the angular momentum for a rigid rotor was the square root of j into j plus 1 times h bar. Right? The angular momentum from a photon was s into s plus 1 times h bar. So going from, let's do initial to some final level, j initial to some j final, right? The change in the angular momentum would be j final times j final plus 1 times h bar minus square root of j initial times j initial plus 1 times h bar. That will be the change in the angular momentum, right? And that change in angular momentum should be equal to the angular momentum of a photon. Oh, you can't see it. There. So the change in angular momentum for the molecule should be equal to the angular momentum from the photon. So let me just make that explicit from photon, because everything must be conserved. All right. So we know that S is 1, little s. So this means that the angular momentum here would be 1 into 1 plus 1 times h bar, which is basically the square root of 2 times h bar. That's this part here. Any questions on this so far? So let's do a similar exercise that we did with energies to find out what are the various changes in angular momentum we can get. So find JF for the following JI. So let's do JI equals 0, JI equals 1, and JI equals 2. So we're using this equation here. We know this part will be square root of 2 times h bar. And so we need to find JF for these different values of JI. So spend some time. Actually, let me do the first one. I'll do the first one to just show you how quickly these are done. So in the first case, JI is 0. So we have the square root of JF into JF plus 1, right? Minus the square root of 0 into 0 plus 1, which is just 0. And that is equal to the square root of 2 into h bar. Sorry, there's an h bar there. Okay, so the h bars would cancel out, so we don't have to worry about the h bar. So somehow there's a value for JF where JF into JF plus 1 is equal to the square root of 2, right? Well, we know that J's could be 0, 1, 2, 3. It could only be whole numbers. So that's the only numbers that we're going to try. So all we got to do is try to plug in numbers in here to figure out which one comes out. And if we do that, we find that the one that makes this whole equation work is JF equals 1. Right? So I'm just going to go up back here and put, if JI is equal to 0, that means that JF should be 1. So try that with the second and the third one, and then you can type your answers in chat, and then we'll gain some insight into this whole situation. When we come up with these sort of exercises, the what am I trying to get at? There's always some like insight that we gain from them that we're going to use going forward. But have we figured out the answers to the second and third one? What are the possible JF values for JI equals 1? Wait, something's wrong. Did I do my math right?
This is where I got stuck too.
Huh. So if this is 2, 2 plus 1 is 3, 2, 3 is 6. Hmm. Ha. Something's wrong here. And I can't see what went wrong. So my insight here was this was supposed to come out to be 2, sorry. And the other one's supposed to come out to be 3. But now I'm trying to figure out how that is and why it's not working.
Dr. Tulai,
Yes.
I'm kind of confused on the first step because when we did the ji is equal to 0, we got square root of 2, right? And
Yeah.
then for the second one, the first part should be square root of 2. And then for the second part, like the 1 times 1 plus 1, shouldn't that be root 2? And then they cancel and then it should be 0.
And what should be 0,
I'm
sorry?
not sure.
Okay.
So like the first step.
So what we're doing here is the angular momentum from the final state minus the angular momentum from the initial state should be the angular momentum from the photon, right? Conservation of angular momentum. And then we talked about how S is 1 for a photon. So that this 1 times 1 plus 1 is 2. So this becomes square root of 2 times h bar, right? So that's where this square root of 2 comes from, here and here. In the first example, J initial is 0. So this whole thing part's 0. And so JF was just 1. In the second part, J initial was 1. Right? So we're trying to find which comes out to be square root of 2. And then, so this becomes 2 times square root of 2. 2 cubed, which is 8. 2 times 2 is 4, times 2 is 8. But the JF is not coming out to be, sorry, Amber Alert. There's some kind of alert. Where did I go wrong? All right, let's not harp on this too much. I'll try to figure out where I went wrong. But the insight we were trying to gain here was that the only possible levels would have been 2. And here, the only final level would have been 3. And technically, if you were emitting a photon, and so you're losing angular momentum, you would have gotten a possibility of 0 or also a possibility of 1 here. And so the insight really that we should have gained, I'm not sure where we went wrong and I have to check on that. But the change in angular momentum here, sorry, implies that the only possible values that J could change would be plus or minus 1. So J can only change either up or down 1. And the reason why we say plus or minus is it's plus 1 if you absorb a photon, not photon, but photon. And it's minus 1 if you emit a photon. Right? So if you absorb a photon, you must gain that angular momentum. So your own angular momentum goes up by 1. If you emit a photon, you lost the angular momentum that's now in the photon. So your angular momentum goes down by 1. Make sense? Yes? No? Maybe? Okay, so if we come up all the way back to this graph we drew, if your J could only change by 1, then if you start, let's say here, you can only absorb this photon, not, for example, not that. you can't absorb that amount because your J would change by 2. If you start from one of these 3 up here, you can only absorb that amount. If you start from any one of these 5 up here, you can only observe sort of that amount. Does that make sense? And the reason you can only observe that amount is because you need to conserve angular momentum. So we talked about the energy conservation. Now we talked about the angular momentum conservation. And then there's a final, the final thing that we need to worry about was this transition dipole moment. Any questions on those two so far before we look at the transition dipole moment? I will look at the J business and probably update on Thursday and see where I went wrong. But then finally, let's look at M. Remember, M was the transition dipole moment. Okay. So we know that M is this integral between sort of the final wave function, the operator, the transition dipole operator, and the initial wave function. Now, I told you what this operator is, and we can go and find this integral and all of that, and it'll probably take us a whole day. Can we use a simple picture to try to figure out whether this M is going to be 0 or not? Can we use a simple picture? Well, this is rotation, right? So what this means is the dipole changing? That's all this integral is telling us. You have an initial state and a final state and a dipole in between. Is the dipole changing from the initial to the final state? That's how you can read an integral like this, right? So what we need to ask ourselves, without even solving for that integral, can we just figure out whether the dipole is going to change or not, right? So let's look at a molecule that's rotating. Let's look at, I don't know, this molecule that's going to rotate like that. So in the end, it will be, I don't know, it rotates a little bit, and it's not like that. What if this molecule was non-polar? What's the dipole moment over here? No dipole. What's the dipole moment over here? No dipole. So if you're a non-polar molecule, like it is here, and you rotate, there is no dipole moment change. This means that M would be 0 or it's not observed. Right? Remember we said that the intensity is related to M. So if M is 0, this rotation will have 0 intensity in the spectrum. Does that make sense? All right. Let's talk about a polar molecule. So same situation. We have one atom here, and I'm going to just use a different color because it's polar, right? So this is rotating this way, rotating that way. And so after a while, we'll have maybe that, and they're rotating. Now, let's just, since this is polar, maybe that one has a slightly positive charge, right? And this one has a slightly negative charge. So our dipole moment, right, will point in this direction. And then in this example, the dipole moment will point in that direction. So the dipole moment, the dipole moment changes. So here, dipole points to left. Here, as it rotates, dipole moment changes. So what's the insight here? Well, we know then that M is not equal to 0 because there's a dipole moment that changes, right? So this is definitely going to be observed. And we're talking about rotational spectrum here. So what we've gained from this is we can only observe rotational, or let's call it pure rotational spectra of polar molecules. If your molecule is nonpolar, you cannot see the rotational spectrum. I told you, you may not have done a rotational spectroscopy, pure rotational spectroscopy in any of your courses. I don't think. Maybe you have. I have no idea what you did in your courses. But I mentioned that every single one of you have a rotational spectrum, not a spectrometer, because you actually don't have a spectrum from it, but you have a rotational molecular rotational instrument in your homes, right? It says microwave spectroscopy. You all have microwaves. We just learned that rotational stuff, molecular rotation, can only change if the molecule is polar. So I want you to think about this. If I give you a container of, what's a good nonpolar molecule? I can't even think of one. Liquid nitrogen. Yeah, why not? Liquid nitrogen, because it's nonpolar, right? N2 molecule. And you stick that liquid nitrogen in your microwave. I don't recommend doing this experiment, by the way. And you turn on your microwave. Will the liquid nitrogen change its temperature? No. But do we understand now why water molecules in a microwave change its temperature? Because the microwave energy increases the rotational energy of the water molecules, and temperature is related to motion. So, you know, the more and more energy it collects, the faster and faster it rotates, the hotter and hotter it gets.
Does the magnitude of the dipole have any effect on rotation, or does it just
Yeah.
have to be present?
Technically, it's the change of the dipole moment, but so yes, that would be affected by the magnitude of the dipole moment as well. The stronger the magnitude of dipole moment, the more strongly it will interact with your microwaves, and the more likely it is that it absorbs those radiation. The weaker the dipole moment, the less likely it absorbs those photons. Does this all make sense? You can all retrofit your microwaves with little sensors to actually detect these things.
Are the dipole moments generated from like London dispersion forces enough to?
That I don't know. You'd have to do that experiment, right? I would, with a thing like a microwave, I would think so, because a microwave doesn't just put out a little bit of photons, right? It just like blasts your stuff with photons, and so even if you have a very, very tiny dipole moment, some is going to be absorbed. And the problem is you can't really do this experiment entirely void of like outside interference, because the material that makes up the insides of your microwave would also absorb some photons and also increase their temperature. But that's also kind of why some plastics don't heat up as fast as like ceramics and stuff, because ceramics have like sulfur dioxide, polar bonds, whereas plastics are mostly like CH bonds, and they're like therefore less polar and less likely to heat up. Make sense? I am making this all up. I'm not sure if they're entirely true. I'm not an expert in microwaves or any experiment for that matter. But I think based off of the theory, this is how this all should work. So we learned about microwave spectroscopy, which is basically rotational spectroscopy. We learned that the energy differences here are either h bar squared over I, or 2h bar squared over I, or 3h bar squared over I, and so on and so forth. We know that in the bottom stage, there should be just one energy level. There's 3 energy levels, and J equals 1, 5 and J equals 2, and it increases like that. And we learned that when they absorb, because of the transition dipole moment, they could only jump in by one J value. And finally, we learned that they must be polar, otherwise we won't see anything for pure rotational spectrum. So let's put this all together in to see what a spectrum would look like. So let's put it all together. All right. So in a spectrum, you usually have frequency, right, on the x-axis, which is basically related to energy, right? We know energy and frequency are sort of just a constant. And then on the y-axis is usually, let's go with intensity. Okay. So let's assume this is a polar molecule, because if it's non-polar, we would just see nothing. So let's assume this is polar. All right. First, we're going to look at this j equals 0 to j equals 1, right? That energy would occur at h bar squared over I. And there's only one energy state at j equals 0. So we have to take that into consideration. So the energy is h bar squared over I, because that's the difference. All right, so let's come back to our spectrum. Right, we're going to plot, maybe this is h bar squared over I right there. And I don't know, this is going to be my spectrum. I'm drawing it small because there's only one state from j equals 0 to j equals 1. Now, in every other spectroscopy, that would be all that you would see, because in most spectroscopy, if you look at an energy diagram like this, only the lowest energy is filled, right? Because you're at room temperature, the other energies are too high in energy, so all the molecules will only be in the ground state. That's for most spectroscopy, including vibrational and electronic. But rotational one, the rotational energies are so low that that's not true. This one would be filled, that one would be filled, even some of those will be filled. It depends on the specific temperature you're at, right? Molecules are always rotating at various speeds, and so these will also be filled. So if the j equals 1 is filled, there are 3 possibilities there, and that energy would occur at 2h bar squared over I. So we have another possibility here at 2h bar squared over I, right? And that will probably be bigger because there are 3 different possibilities to start out there. You can see how this continues to go, right? 3h bar squared over I, probably be even taller. 4h bar squared over I, and so on and so on. You see how this continues. Eventually, you'll come to a point where all of the, I'm not going to be able to draw this properly. You get the idea. But then eventually, as you get to higher and higher rotational energy, unless you're at a very high temperature, they're not going to be filled. So you don't have as many molecules at starting out there. So then this starts to go back down again. So let me just finish this up by adding, this goes from 0 to 1 for J, 1 to 2, 2 to 3, 3 to 4, and so on. And so if you get a pure rotational spectrum, that's what it should look like.
So what actually, I know like with electron orbitals and stuff, the electron actually occupies the separate energy levels in the separate orbitals. What's actually occupying those separate energy levels here?
The molecules themselves.
Okay.
Remember, the rotational energy levels determines how fast the molecule is rotating.
Mm-hmm.
At the very lowest level, actually, the very lowest level, if you remember, there is no rotation at all. Remember when we did the wave function? For L equals 0, there was no motion at all. It was just like a ring.
Mm-hmm.
And then for J equals 1, it'll be a slow rotation. And then J equals 2 will be a faster rotation, and so on and so forth. So as you're going up and up and up, the molecules are, basically the different J levels tell you how fast the molecules are rotating. But again, this is all quantum mechanics. Picturing the molecules actually physically rotating is a hard thing to do, because it's actually rotating as a wave function, the whole molecule as a single wave function rotating.
What the J levels make sorry. Okay, I'm unmuted. The J levels make sense, but what about like the separate like sub levels, the MJ levels?
Remember the MJ determines what did the MJ do? Whether they're rotating clockwise or anti-clockwise.
Okay.
I'm trying to remember what else the MJ, but yeah, you can play around with that wave function to give a idea of what the different MJs also do.
Mhm.
But if I remember correctly, the various MJs, it's a Z component. It's how the rotation aligns with some axis, right? Because you rotate, if you can see my finger, you're rotating in one sort of 2 dimensions. So how does that rotation aligns with some other axis, the Z axis? That's what the MJ determines. And basically the negative and positive determines whether it's going clockwise or counterclockwise along that axis. So yeah, we learned about microwave spectroscopy and the theory of how microwaves heat our food up. Any other questions on rotational spectroscopy? No? All right, so let's see if I have anything else in my notes about that. I'm not gonna insult your intelligence, but I can't just leave it here. I have to ask you some questions. So, which of the following will be visible in a microwave spectrum? Let's do, well, you guys know that one. I don't know. It's hard for me to come up with small molecules. But yeah, let's do some of these. And maybe you guys can do this quickly. So if you want to unmute, then we'll roll through them. H2O. Or you can shake your head. Yes. CH4. Nope. NH3. Yep. O2. No. And N2. No. There we go. So that basically tells us, well, I mean, you guys know how to figure out polar and non-polar molecules. And okay, so that's it for microwave spectroscopy. Let's move to the next level up from that, which is vibrational spectroscopy. So vibrational, or because it observes in the infrared region, people call it infrared spectroscopy. All right. Not only is it increasing in energy, but it also actually increases in complexity a little bit. For rotational, it's easy. Something rotating. My question to you here is, how many ways, not waves, ways, can a molecule vibrate? So let's imagine we have, I don't know, I'm just going to do 3 atoms. This is one atom connected to this atom, connected to some other atom. Doesn't matter what. These are our 3 atoms, right? How many ways can this molecule vibrate? Well, if you think about it, right, you have this atom here that can vibrate, but it's not a good color, blue. There's an x-axis, y-axis, and z-axis, right? So x, y, z. So when this atom moves, it can move in each of those 3 directions. Same for this atom. And same for this atom. Right? If we call these atom 1, 2, and 3, these will move basically in, sorry, all this should be 1. 1, this could move in 3 dimensions, x2, y2, z2, and this could move in 3 dimensions, x3, y3, z3. right? So our answer to this question is, if there are n atoms, then there are 3 times n, because each atom could move in 3 dimensions, 3n degrees of freedom is what people call them, degrees of freedom. Basically 3 times n possibilities of each of the atoms vibrating and moving. Okay. However, let's say atom 1 is moving in the x direction, atom 2 is also moving in the x direction, and atom 3 is also moving in the x direction, then it means the whole molecule is moving in the x direction, right? Similarly, if all of the atoms are moving together in the y direction, the whole molecule would move in the y direction, and same for z. So those 3 different motions, everything moving in the x, or everything moving in the y, or everything moving in the z, those are not vibrations. Those are just the whole molecule moving. Those are translations, right? So 3 of these, of the various degrees of freedoms, are related to translational motion. Which we talked about is much lower in energy. We're not even considering it. We're only looking for vibrations right now. Now, there are 3 other of these 3n different combinations. There are 3 other possibilities where the whole molecule ends up rotating, right? So 3 of these, or 2 for linear molecules, correspond to rotational motion. So what do we end up with after all of this? We end up with 3n minus 6, so 3 for translation and 3 for rotation, for nonlinear molecules. So 3n minus 6, what we call vibrations or vibrational modes for nonlinear molecules. Or for linear molecules, it's 3n minus 5 vibrational modes. By linear molecule, I just mean molecules that form a straight line. CO2, it's a straight line, stuff like that. That's what a linear molecule is. So this is for linear molecules. So something like water, nonlinear, has 3 different atoms, so n equals 3. So let's do that as an example. For water, how many vibrational modes are there? Well, it's nonlinear, so it's 3n minus 6. N is 3, so that'll be 3 times 3 minus 6. 3 3 is 9, so 3 different modes. So water has 3 different unique vibrations. Does that all make sense? Okay. Now, does that mean if you stick water in, or any molecule with some number of vibrations, in an infrared spectrometer, you will see all of those vibrations? No. We need to go through the various different properties of light, right, to check off the list. Does it match the does it conserve energy? Does it conserve angular momentum? Does it have the frequency matching, the transition dipole moment property? So we're going to go through each of those to see which vibrations for molecules we can see. So let's start with conservation of energy. So let's look at conservation of energy. And like before, we said that the change in the vibrational energy should be related to the photon, right? The Planck's constant times the frequency in light. All right, so we know that bit. Now, earlier this semester, we tried to model vibrational motion, remember? We tried to model vibrational motion using the harmonic oscillator. And so from the harmonic oscillator, let's call it just HO, the energy is, so the energy from the harmonic oscillator, if you remember, is n plus a half times h times this different, let's call different frequency. And that frequency there was 1 over 2 pi times the force constant over the reduced mass. Back when we did harmonic oscillator. This frequency is not that frequency, but yeah. However, remember we also use n for the principal quantum numbers for electrons, right? Which has nothing to do with vibrations. And that's the problem with using these letters for multiple things. So instead of using n, I'm just going to use v for vibration. Right? And so those numbers could be 0, 1, 2, 3, and so on. So the vibrational energy of any state will be v plus a half times h times this frequency that comes from the bond. Okay. So what about delta E vibration? Because that's what we're interested in. Remember, it's always going to be a change in the vibration. So let's go from some initial vibrational energy level to some final vibrational energy level. And let's calculate the energy difference there. So the change in vibrational energy will be the final vibrational energy level minus the initial vibrational energy level, right? I can simplify this, I think. So Vf plus a half minus Vi minus a half times h times mu. The plus and minus a half cancel each other out. And so this becomes Vf minus Vi h times mu. So that's the change in vibrational energy. So this is what should correspond to our photon coming in. Everybody with me so far? Okay, so let's do the same exercise that we did earlier. Actually, we don't even have to. This makes it easy. So if we go from 0 to 1, Vi to Vf, 0 to 1, the difference here is 1 times Hv. If we go from 1 to 2, the difference here is also 1 Hv. 2 to 3, it's the same thing. So unlike the rotational spectrum, if you look at energy, right, and we look at the various different V levels, so this is V equals 0, V equals 1, V equals 2, V equals 3, V equals 4, doesn't matter. The difference between all of these are identical. And they're all H times this mu. So unlike rotational spectrum, the differences here, with at least with a harmonic oscillator model, are the same. So let's just put a little note here. Energy differences. Differences are the same. Okay, so that's our conservation of energy. The energy differences between all of them are the same, so we don't have to worry too much about exactly what it's going to be. But can a molecule go from this vibrational state to this one, and then also from this one to this one? Like, what is the rules here now for the other conservation rules? Let's look at it. So our second one is, what about conservation of angular momentum? Well, here's the thing. When we solved for the harmonic oscillator wave function, there was no angular motion in there. Remember? So the angular momentum operator times that wave function is not going to give us a constant times the wave function. So the vibrations themselves is not an eigenvalue of the angular momentum operator. You can think of it as basically being vibrations don't have angular momentum, which makes sense. Angular momentum only can come from circular motion, right? Some kind of spin. But vibrations are just sort of motion back and forth. There is no rotational motion in there, so there's no angular momentum. So we have to skip this one. We have to skip this consideration. Remember, when something's not an eigenfunction, it doesn't mean that it doesn't necessarily have that property, but we just don't know what it is. And if we don't know what it is, then we can't really consider it, right? It could be anything. So we're going to skip it. We're not going to worry about the angular momentum conservation in this one. So that then leaves us with the transition dipole moment consideration. So what about the transitional dipole moment? All right, again, remember that is the integral between the final vibrational state, the dipole moment operator, and the initial vibrational state, kind of like that. Again, what we need to ask is, does the dipole moment change? Does the dipole moment change when a molecule vibrates? That's the question we need to ask. By the way, there is something that I'm not going to prove, but this usually only happens, or let's say usually happens when the change in the number is plus or minus 1. Proving that is a little bit more involved. So we're not going to go into it. We're going to have to figure out integrals and all that. Not now. So we're only going to worry about this green part here that I wrote. Does the dipole moment change when the molecule vibrates? All right. We're going to do the same thing, but so let's look at diatomic molecules. And so we're going to look at non-polar diatomic. And so we're going to have our molecule like that. It's non-polar. And for vibrations, I'm going to just represent the vibrations by arrow. So in this case, we're going to stretch out like this. That's going to be our vibration. So in the end, this molecule will be stretched like that. And then it will start to shrink back. That's what a vibration is, right? We're going to stretch and come back. Does the dipole moment change? That's what we're asking. So in the first case, this whole molecule is nonpolar. So there is no dipole over here. It stretches, still no dipole. So M would be 0. We cannot observe this vibration. Pretty straightforward, right? Let's look at a polar molecule. So these are diatomics. It's not as simple. It's not like all non-polar molecule will have no vibration. That's not true. This is just diatomic, 2 atoms. So let's look at a polar diatomic. We have 1 molecule there, and I don't know. Let's say here's the other part. It's polar, so we need to represent it by 2 different things. Let's say this one's slightly positive, this one's slightly negative. So the overall dipole moment here would be sort of maybe pointing in that direction. As it stretches, right, the bond becomes bigger, kind of like that, still negative, still positive. The molecule will start to come back in now because it stretches out. But in this second case, the dipole moment is longer. Points in the same direction, but it's longer, right? So small dipole, larger dipole. If we're just asking the question, does the dipole moment change? The answer is yes. So yes, we can observe this molecule in the IR. Instead of molecule, let's say we can observe this vibration. We're looking at a very specific vibration. So we talked about the energy difference. We talked about conservation of momentum, angular momentum, which doesn't matter in this example. And now we talked about the dipole, transition dipole moment condition. And we find you cannot see vibrations in non-polar diatomic, but you can in polar diatomic. So molecules like oxygen, N2, those vibrations you will not be able to see in an IR. And I suppose you can test this for yourself, right? Find a liquid non-polar molecule, stick it in the IR machine, see what you see. Should be nothing. It's a little bit more difficult because most diatomic non-polar molecules are all gases. So maybe liquid nitrogen or something. I don't know. Stick it in there, see what you see. Should be nothing. I'm going to pause there because the story doesn't end there. We're talking about diatomic molecules, but what happens when you go to much bigger molecules? We will talk about that on Friday, and that will wrap up vibrational motion. And hopefully we get to talk about electronic transitions. And also rotational vibrational motion, which is like the combination of 2 kinds of motion. But any questions on rotational and or vibrational motions and how they work based off of the various rules? So I hope you are now appreciating the fact, like you're probably wondering, why did we do 3D rigid rotor? Why did we do harmonic oscillator? Well, all of those ideas are now coming back. Those expressions for energy, angular momentum, they're all coming back now to help us understand spectroscopy. And if the course was like 1 month longer, we could cover these all in depth. And I wish it was, but we're trying to squeeze them in this last week. All right, if you don't have any questions, I'll let you go. I have a thing to moderate. But yeah, make sure, try to attend each other's various different presentations for Scholar Showcase. And I wish you all luck in that. See you all Thursday.